I welcome you all to the session of engine system and performance, and before coming to our discussion on today's topic, let me discuss one important thing that we have been discussing for the last two lectures, that is the transport of energy from the engine cylinder. And we have seen that energy should be transferred from the engine cylinder, knowing fully that we are giving or we are supplying some energy which is chemical energy, and even after supplying certain amount of energy, we are converting that energy into useful work. Though the direct conversion is not possible, still we are trying to remove certain amount of energy from the engine cylinder, essentially to save engine components from excessive heating, from their melting and other mechanical failures. Now, we had discussed out of total energy that we are going to supply to the engine, only a part of that engine is utilized or available at the shaft. Remaining energy needs to be transferred from the engine cylinder to the ambience, or we need to supply coolant as well to remove substantial amount of energy, because transfer of energy from engine cylinder into the ambience, I mean the amount of energy that we need to transfer, that we need to remove from engine, if we need to rely on the convective transport from the engine wall or cylinder wall into the ambience, then we need to have several other complex arrangements like extended surfaces, and we really do not know what should be the length, what should be the area of those extended surfaces to have adequate or required amount of energy transfer. So, if we recall, total energy that Q dot that we need to transfer that from the engine, that is, I should say loss, that is Q dot coolant plus Q dot loss through exhaust system, exhaust, plus Q dot oil, that is what we have discussed, right. So, that we had seen this is 2 to 10%, that is even 5 to 15%, and that is 10 to 30%. So, that we have discussed that transfer of energy by oil, that is lubricating oil, is there, because there are a few places or a few spots in the engine block wherein integration of cooling system is not so easy, like piston face. Piston face is exposed to maximum temperature of the engine or engine cycle. Over an engine cycle, maximum temperature develops during combustion process, and piston face is exposed to that temperature, at maximum temperature. So, what is done essentially, that lubricants or lubricant is splashed over the piston face, which in turn removes certain amount of heat from piston face. That part is there. We have discussed about this part in the previous class. Transport of energy by coolant, which is circulated through cooling water jacket, essentially heat transfer in the combustion chamber, that we have discussed. When we have discussed about heat transfer in combustion chamber, we had seen transfer of energy from engine wall or cylinder wall into the coolant. There also we have discussed about that entire or total length of the engine cylinder is not surrounded by cooling water jacket or is not covered by the cooling water jacket. So, there are parts or portions from which heat transfer directly from outer wall of the cylinder to the ambience, that is convective transport of heat, that we have discussed. Now, which is important to know again, this is that loss of energy through exhaust manifold or exhaust gases. See, if we try to recall, we have mentioned that exhaust valve, intake manifold, spark plug and piston face, all these spots, all these places are having high temperature, but as I told today, due to lack of integration of cooling system, it becomes very difficult to remove heat from these areas. But today we shall discuss that exhaust gases, when exhaust gases are leaving from combustion chamber, certain amount of enthalpy gases are taking away from the system. Also when gases are leaving, chemical energy is also getting lost. So, some amount of energy in terms of enthalpy and chemical energy are getting lost through the exhaust system, that is when exhaust gases are leaving. Now, question is, when exhaust gases are leaving through the exhaust manifold is essentially a pipe or tube. So, tube wall or pipe wall will be heated up. So, is there any arrangement so as to remove certain amount of heat from the exhaust manifold wall, so as to increase their life and also to prevent that particular part from excessive heating. Together with that we have discussed briefly that intake manifold or intake system also facilitates to remove certain amount of heat that develops or that generates due to combustion. So, whether heat removal by the intake manifold is adequate or not, even it is adequate, then how or in which capacity heat transfer or heat removal by intake manifold is important for an engine. So, we will discuss these two parts today and then we will solve a numerical problem. So, let us first discuss about heat transfer in intake system. So, you know that so two questions we would like to address today: whether or not intake system facilitates in removing heat that develops due to combustion. Even if intake system is able to remove or transfer certain amount of heat, then in which capacity? Let me draw the schematic depiction. So, if we draw the engine, so this is the exhaust valve, this is intake valve, this is TDC, and this is VDC. So, the piston reciprocates between these two locations, that is what we have discussed so many times. As such, you have studied this in your internal combustion engine course. And so, this is the intake manifold. and this is exhaust port or manifold. Now, you can readily understand that this is the combustion chamber, combustion space. So, because of the combustion rise in temperature is of the order of 3000 Kelvin, that is what we have discussed. So, you can understand easily spark plug will be heated up, exhaust manifold will be heated up, because eventually combustion gases will leave through exhaust valve and then exhaust port. Also, because of this location, intake system will be heated up due to rise in temperature during combustion process. So, now as I told you that due to lack of integration of cooling system, we really cannot transfer heat from this part, from this part, from this part using coolant. So, question is, because of this combustion, intake system will be heated up, and if we really do not remove heat from the intake system, then intake system is basically intake manifold. So, intake manifold, intake valve together with, or also if now though carburation is obsolete, but still throttle valve will be there, carburetor will be there. So, considering all these parts or all these parts together form intake system. Now, because of the location, heat rise due to combustion process also will heat up the intake system, and then pipe temperature will increase, pipe of intake system and intake manifold, intake valve temperature will increase. If we do not have provision of having cooling supply, then certainly rise in temperature of the wall of the intake system will lead to overheating of that part, melting of that part, and several other mechanical issues. So, when we are supplying air, or when air is drawn into the engine cylinder during intake stroke for CI engine, or when it is air plus fuel, that is called charge for SI engine, incoming air or incoming air flow, air fuel mixture. So, flow of incoming air or flow of charge will facilitate some sort of heat transfer from wall of the intake manifold to the incipient stream by virtue of convection, forced convection, because when piston comes down from TDC to BDC, pressure falls inside the engine cylinder, will allow certain amount of air if it is CI engine, air fuel mixture if it is SI engine to be drawn into the engine cylinder. So, flow will be there, and that incipient flow or flow of air or flow of charge will facilitate to have or to transfer or to remove certain amount of heat from the heated wall of intake system to the stream itself. Now, question is, so that means the incipient stream will take away certain amount of heat from the heated wall, that way we can have certain amount of energy transport or energy transfer from the combustion chamber itself. So, because of combustion, the system will be heated up, wall temperature will increase, and that temperature will be taken away by the incipient flow or incipient stream of air or air fuel mixture. So, indirectly we can have transfer of energy which will develop inside the combustion chamber because of the combustion by the air stream. Now, question is, when incoming air or incoming charge temperature will increase, this is again sometime or this become favorable for the combustion, because if we can increase preheating of air or preheating of charge, sometime, not sometime, it become, I mean if we have proper design, to some extent preheating is necessary, preheating of incoming air or preheating of charge. Question is, if transfer of energy or transfer of heat from the wall of the intake system to the incipient stream is maximum, then in the intake system itself fuel will try or fuel will evaporate. The moment fuel evaporates, again evaporative cooling will be there. So, essentially you know that transfer of energy from the wall into the incipient stream will be there due to forced convection, normal forced convection. Receiving heat, some fuel will evaporate in the intake system itself, and then evaporative cooling will be there. Question is, this evaporative cooling of fuel, evaporation of fuel droplets or some fuel in the intake system itself has some merits and demerits. So, let me write here that if we go to the next slide, that heat flow from hot wall by convection, that will be there, that is Q equal to H A into T wall minus T gas. So, this is basically T air or T charge. So, I am writing T gas. So, this is convective heat transfer coefficient of the incipient stream. Charge, this is surface area, the area which will be involved for this for the removal of heat. So, this is basically the expression of that very well, very easy. Now, question is, as I told you that consequence from convective heating. So, this is convective heating of incipient air stream or incipient air flow mixture by the heated wall of the intake system. So, it has some advantages, some disadvantages. Advantages, I told you that preheating is necessary, that is if we can increase the temperature of air, that will facilitate efficient combustion inside the combustion chamber. On the other hand, disadvantages are there, because that I told some fuel droplet will evaporate in the intake system itself. Now, if fuel droplet evaporates, evaporative cooling will be there, that is also some sort of advantage, but disadvantage is there, because to first of all increasing the temperature of air will reduce density of air, and then if we basically increase the temperature of air fuel mixture or air by this convective transport of heat from heated wall of intake system, then fuel will evaporate, and then fuel droplet will occupy, or fuel droplet will that displace air. So, basically that when fuel will evaporate, that will displace air. So, essentially reduction of air density or density of air due to high temperature together with displacing of air by the fuel evaporation will reduce air intake. So, that is the disadvantage. So, maybe instead of getting required amount of air for the efficient combustion in the combustion chamber, air that will reach is less. So, it is having sort of disadvantage. So, that we have discussed. Now, this is all about the transfer of energy or transfer of heat or removal of heat by the intake system. That means, if we have understood properly, what we can say, that because of the combustion process rather, high temperature that will develop, that will heat off intake system, and since the intake system will be or intake wall of the intake manifold will be heated up, when air flow will be there, convective transport of heat will flow from heated wall into the incipient stream, that will in a way that will increase the temperature of incipient air. It will promote or facilitate efficient combustion, though it will be having some disadvantages that we have discussed, but in a way indirectly intake manifold is also helping to remove certain amount of heat that will develop due to combustion process. Okay. So, now let us discuss about kind of heat transfer in exhaust system. So, if we go back to the previous slide, we can see this is the exhaust system. So, we have discussed that part is very critical part. That system is very critical system, because that part will be always in contact with hot gases. Though combustion will be there, combustion is just the process is a cyclic process, because in a cycle combustion will be there in one stroke, remaining other strokes are the ideal stroke, but still during combustion excessive rise in temperature will be there, that temperature will heat up the system. In the next stroke, when combustion gases will leave through this path, that hot gases again will rise or will try to increase the temperature of that system. So, that part is very critical part, but again I am repeating, we really do not have the provision of having cooling system therein. So, lack of integration of cooling system in this area makes scenario even more difficult, and that way we have to have some arrangement so as to remove certain amount of heat from that part, and the melting or possible mechanical failure of this part can be prevented or attenuated. So, let us discuss now. So, what you can see that through this pipe or system. So, let me draw here, essentially that is the intake manifold. So, this is the intake valve, exhaust valve. So, this is exhaust manifold, sorry, this is exhaust manifold and this is exhaust valve. So, gas flow will be there. So, can't we apply normal forced convection model to estimate qualitative amount of heat that will be taken away by this gases. So, basically that this wall will be heated up because of the combustion process. Now, when combustion gases will be leaving, maybe that combustion gases can take away certain amount of heat from the exhaust valve as well as from the wall of the exhaust system. Normal forced convection flow model, but we can apply normal forced convection model with some modification. Modification is there that the flow is not steady. So, flow of is not steady, flow is cyclic rather pulsatile, right. So, that means we can apply normal forced convection model with some modification, that is the flow is pulsatile, because only flow will be there during exhaust stroke, remaining three and during remaining other 3 strokes no flow will be there. So, that means we can apply and that too that when piston will be coming back from BDC to TDC, we can assume the flow will remain more or less steady, but in a cyclic over an engine cycle this flow is pulsatile, right. over an engine cycle we have to consider. So, over an engine cycle flow of combustion gases through exhaust manifold is not steady, rather pulsatile. So, we can modify normal forced convection model so as to take into account the pulsatile nature of the flow to estimate the heat transfer from the heated wall from the valve to the outgoing gases gas flow. Now, one modification is there, as I told you that it is not possible to have a cooling system in this part. One arrangement which is typically considered for automobile engines and also for large stationary engines. What is done, that this exhaust valve is having, or exhaust valve typically in automobile engines and large stationary engines, exhaust valve has hollow stem and that stem contains liquid sodium. So, that is the modification. So, for automobile engines and large stationary engines, exhaust valve has hollow stem containing liquid sodium. So, let me write in word. So, let me discuss why do we need to keep liquid sodium, and keeping liquid sodium, does it help to remove more heat? So, that I will discuss, right. So, basically that you know very well that exhaust system is having 400 to 600 degree Celsius temperature for SI engine large, but it is having for CI engine temperature is 200 to 500 degree Celsius for the CI engine. That is, when there is a steady state flow of exhaust gases, combustion gases, rise in temperature of this part for SI engine is 400 to 600 degree Celsius, whereas temperature rise of this part for a CI engine during steady state flow of exhaust gases is in this range 200 to 500 degree Celsius. So, essentially you have to remove temperature so as to the system can run for a longer time, and we can prevent mechanical failure of these parts. There are many parts: exhaust valve, valve stem, exhaust manifold wall, all this. So, now question is, this is very important, I have written over here that for automobile engine and large stationary engines, exhaust valve has hollow stem containing liquid sodium. Now, in which capacity liquid sodium will help to remove better heat? So, let me tell you one thing, hollow stem will if we have hollow stem, that is essentially you are trying to increase the area. So, it will hollow stem will help to have more conductive transport of heat. Now, we are supplying liquid, or we are keeping liquid sodium in the hollow stem, and that liquid sodium employs phase change heat transfer, right. So, basically that heat pipes. So, basically the concept of heat pipe is employed over here, since hollow stem is having liquid sodium. So, liquid sodium, that means we are trying to have, or we are trying to employ heat pipe in this system, liquid sodium, when liquid sodium in contact with the heated part will evaporate and then condense back to liquid to the low temperature part of the exhaust manifold. And since phase change heat transfer is more effective than normal conduction, phase change heat transfer is so effective that it can remove heat of the order of 4000 watt per meter square surface area. And keeping liquid sodium in hollow stem will also follow phase change heat transfer, and as if had you not considered liquid sodium in this hollow stem, only conductive transport of heat would be there through the hollow stem, but keeping this liquid sodium we are in a way trying to employ phase change heat transfer, which is more effective to remove heat, which is of the order of 4000 watt per meter square. Effective conduction of this component, that is hollow stem, will be more, and that way we can remove certain amount of heat from this system, that is exhaust system. So, now let us solve one numerical problem to illustrate the concept that we have learned in previous class, that is heat transfer in combustion chamber. So, let me read out the problem statement here first. So, problem statement is like this: a 2 liter 4 stroke SI engine operating at 2400 rpm using gasoline. A 2 liter 4 stroke SI engine operating at 2400 rpm using gasoline has 4 cylinders and volumetric efficiency of 80%. The engine's bore diameter and stroke length are related as this. So, this is the relation between bore diameter and stroke length of the engine, that is what we can see. So, this is the relation that we can see. At a given temporal instant of the engine cycle, the gas temperature in the combustion chamber is 1900 degree Celsius, while the cylinder inner wall temperature is 180 degree Celsius. Try to understand, we have discussed that the temperature of the inner wall of cylinder will be within this range 180 to 200 degree Celsius, and rise in temperature in the combustion chamber is of the order of also 3000 Kelvin. What we can see in from the statement is also in that range. Calculate the convective heat transfer rate to the cylinder inner wall at that temporal instant. Dynamic viscosity and thermal coefficient of gas, this is thermal conductivity, it should be thermal conductivity. So, this is thermal conductivity. So, please read this thermal conductivity of the gas at 1900 degree Celsius are 5 into 10 power minus 5 Pascal second and 0.085 watt per meter Kelvin respectively. These two constants are given C1 and C2. Essentially, if you try to recall, these two constants are needed to calculate Nusselt number, knowing the value of or knowing the Reynolds number. So, we have to solve this problem. Essentially, what we need to do, we need to know a qualitative estimate of convective transfer of heat or transport of heat from the gas to the inner wall of the cylinder, right. So, let us solve the problem. So, first of all we have to calculate displacement volume. Displacement volume Vd equal to pi by 4 into bore's diameter square into stroke length. So, this is stroke length. Right. So, if we put the value now, so it is given pi by 4 into B is this. So, it should be 1 upon 1.05 square into S cube. So, that is the expression. What about Vd? So, displacement volume per cylinder. because the engine we are discussing today is a multi-cylinder engine, because the engine has 4 cylinders. So, this is, so displacement volume per cylinder is V d. Now, what is V d? Because it is given 2 liter. So, essentially 2 into 1000 cc divided by 4 is V d. So, if we compare these two, then we will be getting from here, what about S? So, S is, I am writing the value 8.886 centimeter. So, that means displacement volume per cylinder, which we know from the data given, that is 2000 cc divided by 4, which is nothing but this expression. From there we can calculate S, that is stroke length. Once we calculate stroke length, if we go to the next slide, we can calculate bore diameter. So, stroke length S equal to 8.886 centimeter, then bore diameter, or simply bore, or bore equal to S by 1.05, that is 8.463 centimeter. So, if we draw the schematic depiction, right, you know that if this is the engine cylinder, you know that piston is like this. So, though there is a small clearance or small gap between inner wall of the cylinder and piston outer wall, but still we can assume that the piston diameter is as good as bore. So, this is engine bore. So, this is bore B and this is piston diameter, right. So, this is dP, right, B is bore, dP is piston diameter, right. So, bore is this. So, now we can calculate, next is area of the piston face. So, this is piston face, right. As I told you that though there will be a small gap between cylinder inner wall and piston outer wall, rings are provided with the piston, because so as to remove piston, rather increase life of the piston, that we have discussed. We can approximate dP is almost equal to B. So, area of the piston face is pi by 4 into dP square, and if we put the value of dP, which is nothing but B, we will be getting that equal to 56.26 centimeter square, that equal to 8.463. So, this is area of the piston face. Now, why area of the piston face is needed? That is needed because, you know, try to recall, in the last class we have tried to, you know, calculate Reynolds number, because to establish the flow characteristics inside the engine cylinder and the underlying heat transfer, we must establish the expression of Reynolds number and Nusselt number, and that we could do in the previous class inside the engine cylinder, that is to estimate the convective transport of heat from gas to the inner wall or inner wall of the cylinder. Now, and we could define Reynolds number knowing area of the piston face, that is why this is important. So, this is AP. Okay. So, now what about mass flow rate of air into the cylinder? Because Reynolds number, if you try to recall, that is mass flow rate of air plus mass flow rate of fuel divided by AP. So, that will give velocity scale into bore divided by mu g, right. So, this is the dynamic viscosity of the gas in the cylinder, right. So, now we can calculate mass flow rate of fuel mass flow rate of air m dot A equal to volumetric efficiency into rho A into displacement volume into RPM divided by n, small n. Small n is number of revolution per cycle. And then if we calculate, if we use the value of volumetric efficiency, that is 0.8, density of air is 1.181 kg per meter cube, displacement volume per cylinder. So, this is mass flow rate of air per cylinder we are calculating, per cylinder, that is 5 into 10 power minus 4, that is meter cube, and then 2400 and 4 stroke cycle engine. So, there is 2 revolution per cycle. So, this n is 2. So, this is the expression of m dot A. So, this is m dot A, and that will come out as 9.448 into 10 power minus 3 kg per second. Just you check unit. So, this is kg per meter cube, this is meter cube will get cancelled, and this is revolution per minute. So, we have to convert per second. So, that would be into 60. If you, because this is RPM, revolution per minute, so divided by 60, it will be per second, and 2 revolutions, so revolution will get cancelled. So, this is kg per second. Now, air fuel ratio actual, it is given as 13.05. So, let me go back to here. You can consider air fuel ratio actual equal to 13.05. So, if we know air fuel ratio actual equal to 13.05, we have calculated m dot A. So, m dot F, that is mass flow rate of fuel per cylinder equal to will be equal to m dot A divided by air fuel actual. Just if we plug in the value, we will be getting 7.239 into 10 power minus 4 kg per second. So, now knowing the mass flow rate of, so let me box. So, mass flow rate of fuel we have calculated, mass flow rate of air we have calculated, we know we have calculated area of the piston face, we know B, we know mu dynamic viscosity, then we can calculate Reynolds number. So, if we plug in the value all these in Reynolds number, that is Reynolds number, that will be equal to m dot A plus m dot F divided by AP into B by mu G. It would be 3060.5. So, that means if we plug in the value of mass flow rate of fuel, that is this, mass flow rate of air, that is this, you can understand mass flow rate of air is 9.448 into 10 power minus 3, wherein mass flow rate of air is 9.448 into 10 power minus 3, whereas mass flow rate of fuel is 7.239 10 power minus 4. So, less, 1 order less, and that should be. So, that means our calculation is in the right direction, and we have already calculated area of the piston is this. So, if we plug in all these values, then we will be getting Reynolds number this. Now, had we calculated Reynolds number, try to recall Nusselt number, that will give us an estimate about the qualitative rate of convective heat transfer from the gas to the inner wall of the cylinder. So, that equal to H g then B by K g. So, this is thermal conductivity of the gas, thermal conductivity of gas in the cylinder. So, we really do not know about H g, that we have to calculate, but we know B. So, that is equal to C 1 Reynolds number power C 2. So, Reynolds number that we have already calculated, if we go back to this slide, C 1 and C 2, these two constants are given 0.085 and 0.80. So, if we plug in the value, that is 0.085 into 3060.5 power 0.80, and then it would be coming as 52.245. So, that means Hg into B divided by Kg equal to 52.245. So, we will be getting Hg equal to, I am writing directly, that is 52.47 watt per meter square Kelvin, because Kg, the value of Kg is given here, that is 0.085 watt per meter Kelvin. So, that is 0.085, right. So, this is watt per meter. So, this is watt per meter Kelvin by meter, right. So, this is watt per meter square Kelvin, right. So, this is watt per meter Kelvin by meter is coming down. So, watt per meter square Kelvin. So, now have we calculated Hg, next we calculate the convective heat transfer rate, that is convective heat transfer from the gas to the inner wall of the cylinder, that is, per unit area, if we try to express, because we do not have any idea about the area. So, Q dot equal to Q dot by A equal to Hg into Tg minus Tw. So, Hg that we have calculated 52.47 into 1900 plus 273 minus 180 plus 273, unit would be watt per meter square, and this is coming as 90.25, that is watt per meter square. So, if you would like to summarize, so you can understand this is the amount of, so this is basically qualitative, this is not again quantification of convective heat transfer, that I have already mentioned in the previous class. If we need to quantify convective heat transfer rate even in the even inside the engine cylinder, outside the engine cylinder, we need to go for computation. So, qualitatively we could calculate convective heat transfer from gas to the inner wall of the cylinder using some correlation based on the Reynolds number and Nusselt number, and this is coming as 19.25 watt per meter square. So, to summarize today's discussion, we have discussed about the role of both intake and exhaust system to remove certain amount of heat which develops due to combustion. Thereafter, we have solved a numerical problem just to illustrate the conceptual part that we have learned on heat transfer in combustion chamber. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.